The code that breaches your product may be a dependency you never knew you had. You didn't review it, you might not even have added it directly, but it runs inside your application, your build pipeline, or your production environment. The package came from a familiar registry with thousands of GitHub stars. The vulnerability scanner found nothing critical, so you trust it. And your trust is exactly what supply chain attackers exploit. In March 2024, an engineer benchmarking a Linux machine noticed something odd. As such, logins were taking about half a second longer than they should. He started digging and uncovered a backdoor in XZ Utils. It is a tiny compression library that ships with nearly every Linux distribution. Nobody hacked a server to plant it. A contributor calling himself XZ had spent 2 years patiently helping a single burned-out maintainer. He fixed bugs, reviewed patches, and earned trust, step by step, until he got maintainer rights. And then he shipped the backdoor in an official release. Loads of servers were weeks away from granting an attacker remote access, and we caught it by pure luck. That's what trust by default costs. So today, let's talk about taking trust out of the equation. Zero trust for open source. And near the end, I'll show you a 5-stage model you can use to judge how much control your organization really has over its open source supply chain. Right, so what is wrong with open source? Nothing is wrong with open source. It's fabulous. The problem is the sheer volume and total lack of control. An average organization depends on thousands of open source components. Some are added directly. Many arrive as transitive dependencies, and the organization usually controls none of them. You don't control who maintains the project. You don't control how maintainers secure their accounts. You don't control the project's build infrastructure. You don't control how releases are published. You don't control how quickly vulnerabilities are fixed. And you don't control whether the project will still be maintained next year. Developers don't usually investigate each project. They look at the docs, check the download count, and maybe they glance at the number of the GitHub stars, whatever, and then they add the dependency and continue working. But this creates a dangerous shortcut. Trust becomes a security control. A popular project feels safe. A recognized maintainer feels safe. An official registry feels safe. A clean vulnerability scan feels safe. But none of these things prove that the package in front of you is safe. Yeah, but the scanner shows 0 CVs. Yeah, and what does it prove exactly? It just proves that the scanner did not find a match between the components it identified and the vulnerability data it knows about. This is good, no doubt. But it doesn't prove that the package contains no malicious code, that the publisher's account was not compromised, that the build server was clean, that the released artifact matches the public source code. A package can be completely clean, according to a vulnerability scanner, and still be dangerous. Attackers have several ways to make that happen. Most of them fall into 3 categories. The first category is when the trusted person fails. Then, the trusted delivery path fails, or the trusted dependency changes underneath you. Let's begin with the person behind the project. One of the clearest examples is the XZ Utils Backdoor. The attacker did not merely exploit a bug inside XZ Utils. The attacker exploited the trust surrounding the project. The project had a strong reputation. The contributor appeared helpful. The changes passed through what looked like a normal development process, and everything looked legitimate because the attacker had worked hard to become part of the legitimate process. But an attacker does not always need to become a maintainer. Sometimes stealing a maintainer's account is enough. That happened when an ESLint maintainer's NPM account was compromised. Attackers used the trusted account to publish malicious package versions. Their installation scripts attempted to steal NPM credentials from developers' configuration files. From a developer's perspective, the package had the correct name. It came from NPM and it appeared to belong to a trusted project. The identity looked legitimate because the real identity had been hijacked. And this gives us the first important lesson. You cannot permanently trust a package simply because you trusted its maintainers yesterday. Okay, suppose the maintainers are trustworthy and the source code is clean. But you still have another problem. The infrastructure used to build and distribute the package may be compromised. Attackers once compromised a SourceForge mirror and replaced a legitimate PHP MyAdmin archive with a backdoored version. Users were not downloading software from an obviously malicious website. They were downloading a familiar project from what appeared to be a legitimate distribution location. The trusted delivery path had become the attack. A similar risk exists in package registries. An attacker obtained publishing access to UA parser.js and released malware-infected versions of the package. The malicious versions affected developer and CI environments. Some affected projects did not even use UA parser directly. It arrived through another dependency. Those teams did not necessarily choose the malicious package. Another package chose it for them. Build infrastructure can also be targeted. In the webmin incident, attackers compromised the project's build server and inserted a backdoor into official releases. The source code visible on GitHub remained clean. A developer could inspect the repository and find nothing suspicious. But the released artifact did not match the public source. And that creates an uncomfortable question. When you download a package, what exactly are you trusting? The repository, the maintainer, the build workflow, the registry, the mirror? In practice, you are trusting all of them. And one compromised link may be enough. The third category is especially dangerous because everything may begin legitimately. You select a trusted package. The package works. The project has a healthy history. And then something changes. The event stream package is a classic example. An attacker gained maintainership of the trusted package and introduced a malicious dependency. That dependency was designed to affect the co-pay cryptocurrency wallet application and steal wallet credentials and private keys. The attack did not need every event stream user to be an interesting target. It only needed the malicious code to reach one valuable application through the dependency tree. This is why transitive dependencies matter. Your direct dependency may be trustworthy, but it can bring in another package, and that package can bring in 5 more. And somewhere deep inside that tree may be the code nobody on your team has ever evaluated. Dependencies can also disappear. In the left-pad incident, a maintainer unpublished more than 250 NPM modules, including the tiny but widely used left-pad package. And builds across the ecosystem began failing. There was no malware, no CVE, but organizations had allowed an external package to become critical infrastructure without having a reliable replacement or recovery plan. And then there is typo squatting. Attackers published packages with names that closely resemble popular dependencies. A developer mistypes one character, installs the wrong package, and executes malicious code. The cross-env campaign used this technique on NPM. Attackers published packages with names similar to legitimate dependencies and used them to steal environment variables and credentials. And sometimes nothing is actively compromised. A project is simply abandoned. The Boa web server was discontinued years ago, but remained embedded in various devices and software development kits. When vulnerabilities appeared, there was no active upstream project ready to fix them. The software was still in production. The maintainers were gone. No attacker needed to break into anything. Time itself had become the risk. These incidents look different, but they all exploit the same weakness: automatic trust. But trust does not automatically transfer from one person's system or release to the next. And this is where zero trust becomes useful. Zero trust is based on one simple principle: no user, device, or software should be trusted automatically. Traditional security often focuses on building a strong perimeter around a system, keep attackers outside, and everything inside can be treated as trusted. With Zero Trust, you don't just settle with building a wall around your system. You assume that the attacker is already inside. So, instead of asking, is this inside our trusted environment? You ask, should this specific action be allowed right now based on the evidence we have? Every identity must be verified. Every action must be authorized. Every component should receive only the permissions it needs. And trust must be continuously reassessed. For open source software, this means that you do not permanently trust the project, maintainer, package, or registry. You evaluate the evidence for every release. Version 2.3 may have been safe, but that does not automatically make version 2.4 safe. Every release must earn trust independently. So what does it look like in practice? First, you do not trust the package origin alone. A package is not safe merely because it came from Maven Central, NPM, or another familiar registry. The registry tells you where you downloaded the package. It does not prove who created it, how it was built, or what happened before publication. Second, you verify identity explicitly. Who published this release? Which repository did it come from? Which workflow built it? Was the artifact signed? Can you verify its provenance? Third, you apply the least privilege. A dependency installation script should not automatically receive unrestricted access to your network, file system, credentials, and build environment. Builds should receive only the secrets and permissions they need. Runtime components should receive only the network, file system, and operating system capabilities they need. Fourth, you assume a breach. A maintainer may be compromised. A registry account may be stolen. A build system may be infected. A distribution mirror may serve a modified file. You design controls around these possibilities instead of treating them as impossible exceptions. Fifth, you evaluate continuously. A dependency that was acceptable 6 months ago may now have a new vulnerability, a new maintainer, a compromised release process, or no active maintenance at all. Approval cannot be permanent. And finally, you contain the damage. If a dependency becomes malicious, it should not automatically gain access to everything around it. You isolate builds, you restrict network access, you protect credentials, you limit runtime permissions, you make the blast radius smaller. Okay, as you analyze the package, you gather evidence. But this leads to another common mistake. Teams adopt one security tool and expect it to answer every security question. But it cannot. Every security signal tells you something useful, but every signal also has limits. A software bill of materials tells you which components are reported as present in an artifact. It does not prove that those components are safe or authentic. A vulnerability scanner identifies known vulnerabilities associated with those components. It does not prove there is no malware, backdoor, or unknown vulnerability. A digital signature can prove that an artifact was signed by a particular identity and has not changed since it was signed. It does not prove that the signer was trustworthy. A stolen signing key can sign malicious software perfectly well. Provenance tells you how and where an artifact was built. It can help you verify that an approved build system produced the release. But provenance does not prove that the original source code was safe. The OpenSSF scorecard evaluates security practices in a source repository. It can highlight risky development practices, but it cannot guarantee that one particular release contains no malicious code. VAX and reachability analysis can help determine whether a known vulnerability can actually affect your application. They help you prioritize remediation. They do not prove that the artifact itself is authentic. A reproducible build can show that the released artifact corresponds to the source code, and that is powerful evidence. But if the source code itself is malicious, a perfectly reproducible build will reproduce the malicious code perfectly. None of these signals are useless. Even more, you need all of them, really. The mistake is expecting that one signal will provide a complete verdict. Zero Trust does not depend on one magical label called safe. It combines independent evidence, signatures, provenance, vulnerability data, project health, reproducibility, and containment. And of course, the more critical the component, the more evidence you should require. Now, to the most interesting part. Where is your organization today? Here is a 5-stage model for gradually introducing zero trust controls into your open source supply chain. Okay, this is not official framework, and it is not a replacement for systems such as Salsa. It is simply a way to understand your current level of control and decide what to improve next. At step 0, developers download whatever they need from wherever they find it. Dependencies may come directly from public registries. Versions may not be pinned. There is no reliable inventory. There are no SBOMs. There's little or no scanning. Nobody can confidently answer which components are running in which services. At this stage, the organization is not managing supply chain risk. It discovers risks through incidents. At step 1, you begin by learning what to use. You maintain a dependency inventory. You generate SBOMs. You pin dependency versions. You scan for known vulnerabilities. You can identify which services contain an affected component when a new advisory appears. And this is a major improvement. But visibility is not control. You now know what entered your system, but you still may have very little control over how it entered. At step 2, you control where dependencies come from and how they are introduced. Developers use approved registries and download methods. External packages may pass through registered proxy or repository manager. Policies define which sources, licenses, package types, and versions are allowed. Critical open source projects are evaluated before adoption. Known malicious packages are blocked. New dependencies may require approval. At this stage, your organization is no longer merely recording what developers downloaded. It is deciding what may enter the environment. At step 3, reputation is no longer enough. You verify signatures and provenance where they are available. You confirm that artifacts were produced by approved build workflows. Builds run in isolated and temporary environments. Credentials are short-lived. Untrusted pull requests do not automatically receive production secrets. Network access is restricted during builds. Deployment policies reject artifacts that lack the required evidence. At this stage, trust is based on verifiable information rather than a package name and a familiar brand. At step 4, open source components must continue earning trust throughout their lifecycle. Every new version is reassessed. New vulnerabilities and malicious package advisories are continuously monitored. Changes in maintainership, release processes, and project activity are reviewed. Critical packages may be rebuilt independently when the risk justifies it. Runtime access is contained. Teams know exactly where each component is deployed. They can rapidly replace, patch, or internally maintain an abandoned dependency. And if the organization depends heavily on critical open source project, it contributes to the project's sustainability. That may mean funding maintainers, contributing engineering work, or purchasing commercial support. At this level, open source is not treated as free external infrastructure that will somehow maintain itself forever. It is treated as part of the organization's real software supply chain. And most importantly, trust is never permanent. Every release must earn it again. Open source is not the enemy, but blind trust is. The goal of zero trust is not to eliminate trust completely. The goal is to replace assumptions with evidence, to limit what components can access, to continuously reassess risks. In the next video, we will turn these principles into concrete CI/CD controls, because understanding zero trust is useful, but eventually somebody needs to implement it. If you liked this video, don't forget to subscribe to our channel, and until next time!